even turn off the lights yet. Why are you tripping?
Good morning, ladies and gentlemen. Thank you for coming to my talk today. Why didn't you turn on the projector, did I?
No. Say when you want the light off.
You can do it right now.
Okay.
I have some very nice results to show you, but right after the abstract deadline, I came up with some analytic solutions which are almost as good as these optimization solutions, so I thought you might like to see, or I'd like to show you these analytic solutions first. So if I press the right button here, we will progress. So I extend the title a little bit. I'm making the deconvolutions compliant with the idea of rigor wavelet. And after doing that, what happens is that the polarity of the deconvolutions is very clear. And as I say, it's an analytic solution, and it depends critically on understanding that there's a rigor wavelet involved. All this optimization stuff never really depended on a rigor wavelet. It just turned it up most of the time. So here's the rigor wavelet. You've all seen this before. We see the rigor wavelet all the time at the water bottom, and we see it on the top of the salt. And often we can see the bottom of the salt, the same rigor wavelet is upside down. And the reason we see it is because some waves go up to the water surface. They go from the gun up to the water surface and come back down. And so we get a ghost, and something similar happens at the receiver. Now, traditional deconvolution creates a spike, tries to create a spike here. And what we're going to do is try to create a spike here in the middle. So here's just an example so you get a feeling for why I'm excited about this. Here's a typical water bottom rigor wavelet, which looks like black, white, and black. This is a bubble, and processing that we've done has turned it into this. And so I'll go back again. You can see the bubble disappears. All decons do that pretty well. But the water bottom has turned into white instead of black, white, black. And we got also kinds of lots of other things interesting to look at too. On this end, we see the top of the salt is white. Down here, we see the bottom of the salt is black. And there's interesting events all over the place. Like here's a white event, and there's a black event. Here's a black event, and here's a white event. There's just a lot to look at. I think I'd like to blink back and forth a few times so you can see it without any labels. See input, output. Trying to guess how many times you'd like to see this. Okay, so now let's see what kinds of things can happen. Okay, so I took 1,000 seismograms from a line in the Gulf of Mexico, and I computed the waveform. I took the inverse of the prediction error filter, and I got this shot waveform. And when you look at the shot waveform, it's kind of disturbing that the beginning, it does not begin off with a rigor wavelet. And so the calculation I did is traditional predictive decon, find the predictive decon filter, take a look at its inverse and see what the inverse looks like, if it looks like the wavelet. It's supposed to look like the wavelet. The basic assumption here is that prediction, everything's minimum phase and this should all work. But as you can see, it doesn't. So this little analytical trick I'm going to tell you about gives us solutions like this. And this is pretty nice, isn't it? This really does look like a rigor wavelet. It's the same amplitude spectrum that's before. It's got a different phase spectrum. I'm going to tell you how to get this new phase spectrum. And then you see some bubbles here. So let's get started. We're going to start from this classical solution, which has all zeros. It's all zeros before the onset there. We're going to start putting in some values that aren't zero. So I'll start just with 4 milliseconds, put in 4 milliseconds. If I put 4 milliseconds in, you're not going to see much change other than the fact that this spike really wants to move over to the origin. And so I'll do this. You'll see it go 1 over to the origin. I'll try 8 milliseconds, not much change. I'll try 16 milliseconds. You're getting a hint of a rigor wavelet starting out. Wow, 32 milliseconds starts to look like a pretty nice rigor wavelet. 64 milliseconds, you're seeing my favorite here now. And I'll double it again, and then I'll quadruple it, and things will get worse after we pass my favorite one. It's like, how many coefficients do you really want before t equals 0? So when we double it once, it doesn't look too bad yet, but when we quadruple it, things start to get bad. You see, we're starting What's starting to happen is that the bubble is turning out up there way ahead of the time. So what really happens is this process creates a more symmetrical looking wavelet around the origin. And you have to choose one parameter, and that parameter is pretty easy to choose. Just measure the distance out to the bubble, which is about 120 milliseconds. It'll be about half that, or 50 milliseconds is this choice of parameter that I'm going to make. Here's an example of something I coded myself. I usually hope to get students to code things, but I had to do this myself. This is a shot profile from the North Sea. It's a little bit weird, but I thought you'd like to see it because everybody knows that these are water bottom multiple reflections, and so the polarity should be alternating on every other one. And so applying this process, if we start from the bottom here, you see a black one and a white one, a black one, 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 a white one. Or if you come starting from the top on this blue line, we see a black one, a white one, a black one, a white one, a black one, a white one, a black one, a white one. So I'm really thrilled by having a nice result like this. Now, there was a lot more could be said about this particular example. I did one filter for all traces. You know, obviously there's some angle dependence. Many other things can be thought about. But it just tests the program. The program works. The program I'm going to tell you about does this job. Oop, I pressed the wrong button. How do I need to come back on?
Type B on the keyboard, see if that does it. There we go.
Thank you. It's a dangerous button. Okay. So why is polarity revealed like this? Well, polarity is revealed because if you deconvolve with the right wavelet, then the seismograph polarity is revealed. It's kind of obvious, isn't it? Okay, so let's go into decon. Now, I realize people don't study decon these days, so I'm going to review a few things. There's basically two methods. The industry is almost always using these time domain methods, which I won't really discuss very much. But there is this Fourier domain method, which I have in my textbook, and I imagine some people do use it. I've used it quite a lot, even in multidimensional problems. And it's nice and analytic. And so I'm going to take this method, this Fourier domain method, and after we finish getting this great result with this Fourier domain method, making it rigor compliant. The original Fourier domain method is not rigor compliant. Then I'm going to show you, once we understand that one, we're going to convert all the time domain methods as well, so everybody will be able to do the magic tricks that I've been doing here. So let's look at two different ways to parameterize the logarithm of a filter. Here's a complex number, it could be a filter. And you can express it in this kind of logarithmic form. Now this looks a little strange. What we have up here is a z transform. Remember that z to the tau is e to the I omega to the tau. Then you realize that this is secretly a Fourier transform of some time domain parameters. So what this Z transform does, this is the summation of the Fourier image. What this Z transform does is just parameterizes a frequency-dependent function. Okay, now we're ready for my one slide with equations on it. And this slide is how we're going to force a wavelet that looks kind of Rickard-like. So the first thing you notice about this U function is that it has an even part and an odd part. And if we add those the even part, of course, Fourier transforms to the amplitude, and the odd part Fourier transforms to the phase. If we add those two even and odd parts, we just get the U function. Back again. Now the way the problem is posed, we're given a spectrum to begin with. That says we're given the even part of U, so we're not allowed total freedom with U. We must restrict ourselves to the given even part of U, but we may play with the odd part, which is the phase part. So along comes Professor Kolmogorov, and he says, for negative times, this function must vanish. Mr. Kolmogorov knows a special theorem that you and I don't know. It's proven in my book. It would take me 5 or 10 minutes to prove it. This theorem says if you can get causality up here in the exponential world, you're going to have causality down here in the real physical world, in the shot waveforms and decon filters. Okay, so from that, he says that's his idea, and so he says the even part plus the odd part, if you add them together, they should vanish for tau less than 0. So that's the Kolmogorov spectral factorization program, and you can choose a plus sign or a minus sign if you want the decon filter or if you want the shot wavelet. They're obviously inverses to each other. What I want to do is change this a little bit. We're going to say Kolmogorov had it mostly right, but he didn't have it all right. Near the origin, we don't want causality, we want a symmetrical wavelet. So what we have to do near the origin is take the odd part and make it smaller, weaken it at small lags. I'm going to be using some kind of a like sine squared weighting function that's going to end at 60 milliseconds. So there you are. That's how it all works. Now, if you have some other decon filter, like maybe your company has a time domain one, let me tell you how you can get the same result. What do you have to do? You have to go get the phase spectrum of your decon filter. That will be an odd function of omega. Bring it into the time domain. Now you have an odd function of time. And at zero lag, near zero lag, within 60 milliseconds, just dampen it down. Now you got a new decon filter, just go ahead and use that. So now that polarity means something, we could agree that maybe white polarity is a hard rock and black polarity is a soft rock. We'll ask the interpreters what they would like, what convention they'd like us to use. You might ask, why didn't we figure this out 40 years ago? Well, because 40 years ago, everyone got interested in migration and they lost interest in deconvolution. That's my answer. So there's two uses for this new trick. I'm going to call it the rigor trick. We can use it as is, just as I've described, to modify conventional deconvolution. Or we can use it in fancy deconvolutions, like the one that my abstract tells you about. Deconvolutions which need a regularization. I had a problem that's described in the abstract of I had a uniqueness problem, and I needed a regularization. And I did not have it at the time I wrote that abstract. So I figured out the regularization. This is the regularization. Just make the odd part a little bit small for lag values less than 60 mils. So here we have my original title slide. Push that up a little bit. And sparsity decon in the log domain with variable gain. There's a lot of equations there, but I want to take you through the definitions so that you'll understand really what problems we're solving. This does give better answers, and I'm going to show you some of the answers that are a little bit better. We seek sparse deconvolutions by using a hyperbolic penalty function. A hyperbola is a parabola near the bottom, so it's like least squares for small residuals, and it's like absolute value function near the asymptotes of the hyperbola, so it's like the L1 norm for larger residuals. We're going to use this U variable, which I might mention, people like to call that quefrency. I don't like it because it sounds too much like frequency and it's in the time domain. So I call it the lag log space. Incidentally, if you look up quefrency on Wikipedia, you'll discover they don't know what Kolmogorov knows, that causality in the exponent, in the log, causality in the log space gives you causality in the physical space. But the other, next, this is probably the most important departure here. You should realize that applying a gain function as a function of time does not commute with applying a filter. And we're going to do that right. So that's probably the main step forward, the main part of the paper. One of several steps forward. And we're going to see the results from that, and we're going to see that if you do the gaming after decon, it will benefit you in two ways, at least in this example. It'll benefit us at low frequencies, and it'll benefit us from the point of view of just noise. So I've been working on this for 2 years, and we got some fabulous results right in the beginning, and I was really excited about that, reported it to sponsors. The polarity was always very clear, but it was random. What would happen is sometimes it would be spiking here, and sometimes it would spike in these other locations. And you change some rather trivial parameter, and it would change the place you'd get the spike. And the net effect was really disturbing. Because if it jumped from here to over here, there seemed to be a big time shift on your seismogram. And it was also annoying to see the polarity change. You can imagine what interpreters would think of that. So I think I lost 3 students while I was working on this because it was frustrating. We didn't know really what was going on, but I figured that out, and now we know the answer to that, and so I'm a happy man today. everything is resolved by this rigor regularization I've just told you about. Okay, so let's see how this works. Here's the data, and here's the filter. And we're going to Fourier transform that to get the residual, or the reflectivity, or the output. This is a function in physical space that's going to be decreasing in strength with time as the echoes get weaker. And the U variables are, of course, our lag log spaces, our adjustable parameters, and we're going to need to measure the penalty of this of the residuals. And so we're going to gain up the physical residual to get what I'm going to call a statistical residual. We're going to apply our penalty function to the statistical residual. That's when we're going to try to sparsify. And we'll try to sparsify this function, which is the hyperbola, which I said it looks like a parabola at the bottom and looks like a straight line, absolute values when the residuals get large. And we'll be taking derivatives of this penalty function in order to minimize it. And the derivative, we call it the soft clip of the residual. I should call it the softly clipped residual. Because, well, that's just a better word for it, the softly clipped residual. Maybe I should have called it the soft residual instead of the soft clip. Okay, then the question is, what should the gain function be? And students ask me that, what do you want for the gain function? I say, well, why don't you start off by putting half the points up in the L2 zone and half in the L1 zone, and see how it works, and then you can play with the strength of the gain that you're going to use. So here we are, we're starting by looking at the output function, and we're going to take its derivative with respect to one of the adjustable parameters. Now, if we've got the wrong output function, we want to gain that up, and here it is, the same thing is gained up. And now we've got the derivative with respect to Q, the statistical gradient. So working through some of these steps here, we end up with this final expression, which is a cross correlation, you see. And since it's a cross correlation, it can be computed in the Fourier domain, and that's all very nice. Now, this is the direction in which we're going to be moving as we're descending. We're actually going the opposite direction, the minus of that direction. Except that there is one restriction. You have to take out that point at zero lag. Because when the gradient vanishes, it will be because the zero lag has been moved out, and all the cross correlation terms will vanish, except that zero lag, which is the point that's removed. And so I'd like to tell you how this relates to normal least squares, problems that everyone's familiar with. In a special case of the L2 norm, it's well known, or it's proven in my textbooks, that the residual, the output residual, is white. Now, in the case of the L2 norm, in the stationary world, the gradient, the gain function is 1. And so this Q is the same as R, the gain is the same as 1, and the softly clipped residual is the same as the residual. So you're ending up with nothing other than the autocorrelation of the residual. So we've taken the standard approach to deconvolution, and it's been generalized in 3 different ways. Now we have non-causal filters, we have the gain in the correct place with respect to the filtering, and we have the notion of sparsity all here. So we're going to compare some results, and I want you to understand that what we call the old result means that you do t-squared gain first, and then you do deconvolution. We have the new result where you do this new kind of decon I've been talking about, and then you do the t-squared gain, and you look at Q. And we're hoping we get the low frequencies a little bit better. So here's the old result, and you can see that there's maybe you cannot see, there's a little low frequency before the water bottom. But you can see there's a little low frequency ahead of this strong event. So that's annoying, and when we do the gain in the correct order with respect to the filtering, we get this thing here, so which is better. And we don't seem to have it on above the water bottom. So that looks like a positive result. And here's a shot waveform estimation. It's a beautiful shot waveform estimation. There is a little bit of noise way out on the side, which you can't see very well, so I've turned up the gain by a factor of 10. When I do that, you see that if we do the gain in the right order, we get a much smaller residual than we get if we do it in the wrong order. The same thing happens over here. So that's all the results I have to show you right now. Seismogram, the conclusion is that seismogram polarity is revealed by rigor compliant deconvolution, and that it's simple to code. And the other conclusion is that gain does not commute with decon, and it should be done afterwards. And I have one or two nice examples of that, but that's about as far as it goes. I'd like to thank the team that I've worked with through the years. The only one who's with me nowadays is Antoine. I'd like to acknowledge people for the data sets and Antoine in particular for visiting Stanford as our consulting professor and doing the coding for me in the last year or so. And thank you for your interest.
21 minutes, pretty close. There's about a minute lost here and there with